Hello and welcome to the forecasting module on models for demands with trends and seasonality. In this module, we are going to be looking specifically at the Winters method based on triple exponential smoothing along with an example. Before we do that, let us first try and visualize the data. So what do you mean by seasonality? By seasonality, what we want to indicate is there is some sort of a repeating pattern within the data that can be observed. We have three graphs here. One is on the monthly auto sales from 2010 to 2017 at the top. On the left bottom, we have Mitsubishi sales data from 2000 to 2004. Then we have Tower Salt example on the right, which is over about 12 periods. In all these three examples, you can see some sort of a repeating pattern. In the first case, we have, for example, sales seems to keep increase and decrease and increase and decrease, increase and decrease, increase, decrease. That seems to be the pattern that seems to keep following. Of course, in the first example, there is also an increasing trend line that can be seen in the past data, and the more recent 4 seasons, there seems to be decreasing trends. So each pattern, we are going to call it as a season. The second example, Mitsubishi, you can see, observe that data seems to be follow a pattern like this. And another season starts and goes like this, another season starts and goes like this. So that seems to be the pattern in this particular instance. Similar type of example seems to have an increasing trend 1, 2, 3, and 4, like this. And then again, it starts at the bottom and then goes up, and starts at the bottom and goes up. Again, there seems to be some sort of an increasing trend in each season. In Tahoe example also, if you actually plot the trend line, it does show an increasing trend also along with seasonality. So within season there's an increase, as well as across season there seems to be an increase in the overall mean. Now, the underlying demand series, what we are assuming, can be captured as follows. The demand dt is nothing but a function of mean mu plus t into c plus epsilon in each time period t. Now the mean mu is nothing but the base signal which excludes any trend and seasonality. Capital T is the trend component and C is a multiplicative seasonal component. So this component is nu, the trend component. The seasonal component. And epsilon is of course the error with mean 0 and variance sigma square. Right. So what we are doing is the mean, of course we don't know the value of mu or t or c. What we are going to do is we're going to estimate mu using the levels and trends using t, and then we're also going to estimate this seasonal component. For this, we're going to make one more assumption that the length of one season is assumed to be exactly p periods. So it's not one season, it is actually any season, any one season. We are going to assume it's exactly p periods. That means all the seasons are of the exact same size. Let's directly jump into the method of triple exponential smoothing. It is an extension of the Holt's method of double exponential smoothing. As you can see from here, the L period ahead forecast made in period t is given as ft, t plus L. That is forecast made in time t for period t plus L is given as Lt plus L into Tt into Ct plus L. Observe that Lt and Tt refers to the past periods level and trend, but the Ct plus L right here indicates the seasonality component of the forecasted period t plus Lth period of the forecasted period t plus L. By extension, we can also write, since we are used to do a single period forecasting, we can simply write this as ft to t plus 1 or ft plus 1 can be given as Lt plus TT into CT plus 1. Yeah. Now let's look at each of it. Of course, the value of L is nothing but the intercept. T is the value of the trend at time T, and C is the value of seasonal component at time T. Each of these is going to be governed by a kind of an exponential model with different smoothing parameters, alpha, beta, and gamma, which you will just see right now. So let us write the expression for level T. So level T we are going to calculate as LT is equal to alpha into dt by Ct plus 1 minus alpha into LT minus 1 plus TT minus 1. This expression is almost similar to the level expression Holt's model, except we have seasonality component right here. The trend will be include a parameter beta times LT minus 1 plus 1 minus beta times TT minus 1. This expression exactly same as the Holt's model. Now comes the new one, which is forecasting for CT plus P. It's given as gamma into dt divided by LT plus 1 minus gamma times CT. Note that in each period T that we are trying to forecast, we are actually computing LT, TT and CT plus P. That is P period in advance. What is the new value of the seasonal component? For all these parameters, alpha, beta and gamma are between 0 to 1. And as with the case for alpha and beta, similar to that, if gamma is small, then it gives, then the model reacts slowly to seasonal changes. So gamma small react slowly to seasonal changes. Now we have the base model with us. So an interesting scenario occurs is we need to estimate the values of the initial values of C, T and L. That is L0, T0 and the initial set of values for C's. So that is what we need to do. Now let us see how to estimate these values. The alpha, beta and gamma is typically assumed as some parameter, or we know how to estimate it based on some sort of optimization model. Let us see how to estimate L0, T0 and C1 to Cp using the data. Now, to estimate L0, T0 and the C values, let us first understand some of these properties. So we are going to take the periodicity P. This means that there is P data points in a season. We have P data points in a season. So in this example that right here, it looks like a data point 1, 2, 3 and 4 forms a season. And data point 5 to 8 forms another season, and so on. Now these are just multipliers, right? The CTs are multipliers. So we have a property saying that when you sum over all T where the T belongs to one season, it should sum to P. This is to just ensure that the proportionalities are equally divided among all the steps all the P points within the same season. And we are going to suppose that we have M cycles or seasons of data. For this forecasting work, we need at least 2 seasons of data. It will be good if you have at least 3 seasons of data so that we can accurately model the seasonal component. And suppose we have M cycles or seasons of data, that means the total data points would be M into P. M cycles or seasons, and then P is the number of data points per season. So this is the first initial step that we need to do. That is estimate what is P and what is M. Having done that, we next go into a multiple step process to estimate our L0, T0 and C1 to P. So first step in doing that is to calculate sample mean Vi for each season. So if you look at the example here, what we want to do is we want to compute for this particular example, we want to compute V1, V2 and V3. That's because we have 3 seasons, season 1, season 2 and season 3, right? So we have season 1, season 2 and season 3. So for each of the season, we need to estimate the mean values V1, V2 and V3. So if we do that, that value is going to be roughly in the middle. We have these 4 points and that is going to be in the midpoint. And since we have 4 periods, that will roughly corresponds to a period right in the middle point. So this will be your V1, V2 and your V3 values. Now, since I know all these midpoint or the mean values, now I have removed the effect of the seasonality. Now all I am having is the mean value, and if the mean is going to be showing an increasing trend, then I can use these values of V1, V2 and V3 to estimate my trend value. And trend value, so now we have multiple data points, so the trend value is nothing but delta y minus divided by delta x. So T naught can be simply given as Vm minus V1 divided by m minus 1 into P, that is delta y divided by delta x. We could have used V2 divided by V1 or etc., but let us, for generalized purpose, let us take the first point and last point until so Vm minus V1 divided by m minus 1 into P. So once I have the T naught, so I know the trend of this line which is passing through the midpoint through the point V1. So I know the trend value is right here, which passes through V1. Now I want to estimate what is the initial value of L0. L0 value is something kind of outside this. You can see x-axis starts at 1, so I wanted 0. So I want this value of L0. To do that, I can simply extrapolate because I already know the value V1. I know the trend at that point, and I know how far this point is from here. So I know the distance from here to here. So I'm going to use that information to compute a L0. So by doing that, the expression for L0 will come out to be V1 minus T0 into P plus 1 divided by 2. Again, remember that L0 is the value at time 0, not time 1, time 0. Now we have initialized T0 and L0 very quickly. Now what we need to estimate next is the seasonal components. For that, step 4, let us compute our d hat of t. Our d hat of t is nothing but a trend line that we want to estimate. So the d hat of t can be simply given as d hat of t is equal to L0 plus t into T0. This is for all t. So the red line here actually represents your d hat of t. So what I'm doing is using this trend line, trying to figure out the values of d1, so d1, d2, d3, d4 hat, rather. This is d1 hat, d2 hat, and so on, all the way up to d12 hat. So that's what I'm trying to estimate here. Now I have the actual data points d1, d2, etc. I have the d hats. I'm going to use that information to compute the seasonality component c hat of t. So c hat of t simply given as dt divided by d hat of t. That is ratio between the demand and the how much this trend component is away from the demand. So that I compute for all values of t. Next, step 6 and 7. So by end of step 7, we'll have the estimates of the seasonal factor coefficient. So before that, we'll do step 6. Now we have to compute the seasonal factor C tilde of j. In C hat of t, I will get seasonal component of all values of t. So in the seasonal factor C tilde of j, what you are going to simply do is average. We're going to simply average the seasonal average the seasonality CTs hat that correspond to similar positions in the cycles. That is the first position of, so I have multiple cycles, we have m cycles. So the first position in cycle 1 plus first position cycle 2 plus first position cycle 3, etc. up to first position cycle m. All those m data values are taken and an average of that is computed. To see it mathematically, we can see the expression C tilde of j can then be given as j equal to 0 to m minus 1 C hat of jp plus 1 divided by m. This is for j equal to 1 to p. Of course, if you remember, m is the number of seasons. Now the last step, where we're going to normalize the data so that the property that the summation of all the c's is equal to p is met. To do that, I'm just going to divide each of the cj's divided by the sum of the cj's, j equal to 1 to p into p. So that will give us the seasonal components. This is for all j equal to 1 to p. So finally, we'll get these cj values, which corresponds to the seasonal component that we want. So at the end of this 7-step process, we'll have initialized and got our values of L0, T0, C1, etc. up to Cp. So this is to the initialize the model. Now, let's take a look at an example to reinforce the steps as well as see how these computations go along. Now let's look at the kind of example that we have here. So we have the data that is given for 12 periods and we have various demand points given. Now using Winter's method, forecast the demand for next 4 periods and evaluate the accuracy of the model. Values of alpha, beta and gamma has also been provided for us. First step in any kind of forecasting exercises that we would like to do is visualize the model. Of course, this example is same as you already seen this chart before. You can see there's an increasing trend, and then again it drops down, and then again there's an increase, and again drops down, again increase. That trend, this short-term patterns, we are calling as seasons. So the preliminary step that we do is, in this particular example, P is equal to 4. That means that 4 data points we have season 1, season 2 and season 3. So each of these season has 4 data points and M is 3 seasons. Right? That is a number of seasons. Now we have to follow the 7-step process to estimate L0, T0 and C1 to P, and then we'll be using the Winter's method using alpha, beta and gamma to do the forecast, and also we'll compute MAD, MSC and MAPE in this example. Let us go step by step in estimating L0, T0 and the seasonal factors. So first step is to compute our VIs. So if you see here, Vi is nothing but the mean, right? So we are going to take, since P is 4, we are going to take the mean of these first 4 values. There's nothing but D1 plus D2 plus D3 plus D4 divided by 4. So 8,000 plus 13,000 plus 23,000 plus 34,000. So that gives a V1 value divided by 4 gives a V1 value of 19,500. So again you take a mean of the next 4 periods, that is your V2, which comes to 22250, and your V3 is the mean of the next season, which comes to 24500. So we have it right here. Let me just divide the screen. Now we have computed V3, V1, V2, V3. Now using that, let us next compute the trend. So T naught, we just define it as Vm minus V1 divided by m minus 1 into P, right? So in our case, it will be simply V3 minus V1 divided by m is 3 minus 1 into 4. You can see all the known parameter values are going to be displayed on the right top. So V3 value I know 24,500, V1 is 19,500, and I can do this simple math to estimate the trend to be 625. So that is your T naught. Now I can then compute my L naught, which is simply given as V1 minus T naught into P plus 1 by 2, which in this case becomes V1 minus 625 into 4 plus 1 by 2, which comes out to be 17937.50. That's your L naught. So now we quickly determined our T naughts as well as our L naught. So that is going to be very useful for all the other steps. Now moving to the next step, let us compute our DTs. The right top here you can see the values of L naught and T naught that we have computed. So in the D hat of T, there is nothing but, we already wrote the expression, D hat of T is nothing but L naught plus T into T naught. This goes for all T. We can just do a simple calculation. Let us take any row just as an illustrative example. Say D hat of 3 will come out to be L naught plus 3 into T naught, which in this case is 17937.5 plus 3 into 625, which comes out to be 19812.5. Or I can do for say D10, D hat of 10, which comes out to be L naught plus 10 into T naught, which is same 17,937.5 plus 10 into 625, which is just a simple trend values. So it comes to 24187.5. So these are the estimates I'm going to get. I need to do it for all the values, D hat of 1 to D hat of 12. I need to do all the values. Once I do that, this table here on the left in red color, we can see the D hat of T values for all the time periods 1 to T, and the same is plotted on the right side, which you are seeing as the D hat of T. So this is your D hat of T. Now we need to compute a C hat of T. C hat of T is simply given as C hat of T is nothing but dt divided by D hat of T. I know the D values, I know D hat values, so I can simply compute my C hat of T. For example, in this case, a C hat of 1 is nothing but D1 divided by D hat of 1, which is 8000 divided by 18562.5, which comes out to be 0.43098. Or I can take another bigger number, say C hat of 8, So this is the first point that I took here. Demand is lesser than d hat of t, but it need not be so because there are some points above d hat of t which has to be. So in that case, you can see that, for example, say c hat of 8, demand is much higher than your d hat of t. So in this case, c hat of 8 would be 38,000 divided by 22937.5, which comes out to be 1.65668. So now we have c hat of t. So we have two more steps remaining, c tilde of j's and cj values. Now we have to compute c tilde of j. Now you can see this table has now increased, so all the c hat of t values are now displayed in this table. Now in computing c tilde of j's, what we are saying is we already know the season. So this is up to 4 is season 1, 5 to 8 is season 2, and 9 to 12 is season 3. So I have all these three values. Now I have to average the values of c hat of t from the same position across all the seasons. So I'm going to take the first value here, here, and here. So that will give me my c tilde of 1. It's nothing but an average of c hat of 1 plus c hat of 5 plus c hat of 9. So this one here, data point 5 is in the same position in the season, that is the first position in the season 2. Data point 9 is the first position in season 3. So I'm taking an average of those three values to get, so I know the values for 0.43098, 0.47478, 0.50928. I take an average of that. I can get a c tilde values of 0.47168. Similarly, I can compute c tilde of 2, c tilde of 3, and c tilde of 4 can be similarly computed. For example, c tilde of 4 will be the average of c4. C tilde of 4 will be average of c hat of 4 plus c hat of 8 plus c hat of 12 divided by 3. So that will give me c tilde of 4. Once I do that, I have 4 values of these c tildes. Right? I don't need to compute for all the periods, just 4 periods. J is 1 to 4. So I have all these 4 values for c tildes. So now I want to normalize the c and obtain the cj values. You already know. Let us take this, let us take the sum of this. So I can use this to figure out the sum of c tilde j's. If I just sum it, j equal to 1 to 4, then the values I'll get is 3.95782. Note that my p is 4, but the sum is coming only 3.9, so I want to normalize it to so that the sum is 4. So it's exactly what I'm going to do. So for example, in this case, c1 is going to be c tilde of 1 divided by the summation of c tilde j into p, which comes out to be 0.47671, marginally higher than the c tilde j's I got. Now similarly, I can compute my c2, c3, and c4, which will complete the initialization process. So the CT values that we have obtained by normalizing is shown here on the last column on the table, which is these 4 values. Now the model is ready for forecasting. I have L0, T0, P and M. I already know my alpha. Alpha is also given as 0.05 and beta is given as 0.1, which is also the value of gamma. So now let us go time by time. Let us start with not time period 1. What we're going to do is start with t equal to 0. At t equal to 0, we need L0, we need T0, both are available above. Right here in the top, I have L0 and T0. Now I can actually do the forecasting. If you look at the forecasting expression, f of t plus 1 is equal to f of f1, which is nothing but Lt plus Tt into C1. So now to use the expression, when t is equal to 0, then this becomes L0 plus T0 into C1, F1 is equal to L0 plus T0 plus into C1. And I know L0, I know T0, I know C1, which is 0.47671. So I can use it to compute the forecast for time period 1, which comes out to be 8,848.87. So that is a forecast for time period 1. So to get the time period 1 forecast, of course, we have to start at time t equal to 0, so that we can get the forecast for time period 1. Up to this is straightforward. But to forecast for time period 2, I need level at time 1, trend at time 1, and C at time 1. That is what we are going to do next. Now, continuing the forecasting, I have removed some tables. So now what you see is only the D hat and CT, only the relevant values. Actually, D hat is not needed, just D and CT is what is needed. Anyway, so now let's go to a time t equal to 1 is what I want to start with. So time t equal to 1, let us compute the values of level. Remember, what we eventually want is F2 is equal to L1 plus T1 into C2. So in this expression, C2 is already known, but L1 and T1 we don't know. So let us just hold on to that thought. So L1 can be computed as alpha into D1 by C1 plus 1 minus alpha into L0 plus T0. Again, I know all these values. I know D1, I know C1, L0 plus T0. So if I compute it, I get a L1 value of 18473.46. T1 is simply given as beta into L1 minus L0 plus 1 minus beta into T0. Remember, for trend 1, I need L1 value, which is right here. And then I have L0, which is also available. And then T0, which is also available. I know the value of beta. So I can compute our T0 to be equal to the new trend value comes out to be 616.096. Now, remember, there's a third step called as CT. So in this case, we need to forecast CT plus P. In this case, comes to 1 plus 4, which is C5. So in period 1, I'm trying to that we will be computing the value of C5. That is the corresponding location, the second cycle. What is the forecasted value of that? So we are pretty much computing C5 in this particular period. So C5 will be simply given as gamma into D1 by L1 plus 1 minus gamma into C1. Again, I know D1, I know L1, I know gamma, I know C1. So using that, we can compute the value of C5 to be 0.472341. So based on the observed value, the value of C5 is slightly differed from the value of C1. We are not done yet. We are not completed the forecasting. So let us do F2, which is nothing but L1 plus T1 into C2. Note that we are multiplying by C2, not C5. C5 is reserved for when we do forecast for fifth period, we'll use C5, but for now we are using only C2, which will come out to be 13151.18. Like this, we can continue the forecasting to obtain the forecast for all the periods up to period 12. So that is what meant by forecasting the past. Remember, forecasting the past. So this table now shows all the values of L, T all the way up to 12 periods, and CT values goes from 5th period to 16th period. Remember, because we are forecasting CT plus P, not just CT plus 1, we are forecasting CT plus P, so we are going all the way up to 16th period for C, and then we can compute the forecast from period 1 to 12. So this is the green is the final forecast values of the past. Now using all these forecasted values, I can, and we already know the original demand values which is in column 2, and then we have the forecast values. Using this, we can do the accuracy measures based only on these parameters: MAD, MSE and MAPE. We know how to do that. Now, what we now need to do next is to forecast the future. That is, we need to figure out what are the values right here. We need to figure out F13, F14, F15 and F16. So let us see how to do that. For that, let us remember where we are. We are at time t equal to 12. We have moved up to that point. So the forecast for the future will be given as forecast at time t for t period t plus L is given as LT plus L into TT into CT plus L. So in our case, we are at time 12, T plus L will be L12 plus L into T12 into CT plus L, where L goes from 1, 2, 3 and 4. That's what we need to do. So in this expression, I can, suppose we set L is equal to 1, we can get forecast at time 12 for time 13 is nothing but L12 plus 1 into T12 into C13. I know the C13, I know the level 12 and trend 12. So if I substitute F13, comes out to be 1, 2, 3, 5, 4.81. Let's take up some other period. Let's take up the next one. So from L equal to 2, I have F12 to 14. Note that now we are again still using L12 into 2 into T12, but my season component changes to 14. So seasonal component is same as the forecasted period, but the level is same as the period at which I am currently right now, the level and trend. We are assuming the level and trend continues the same, but we know the seasonal component 14. Now if we substitute it, we can get this value as 18215.35. Similarly, I can compute for 15th period and 16th period forecasts. The complete table of this example is now seen in this screen. The past values are shown in green of forecast. The future forecast is shown here in blue, what we just computed. The intermediate steps of L2, LT, TT and CTs are shown in black. And the initialization routine which we did to estimate our CT values and L0 values and T0 values are shown in red in the table, and original data points are shown in green. In summary, we have looked at the Winter's method of triple exponential smoothing for handling data with trend and seasonality. Note that there are other variants to get L0 and T0, but not much. This is a really good method also. Thank you.